Welcome to Module 3. Now that you have experimented in introducing changes to your process, let's leverage on those experiments and sustain lasting improvements. On this first lesson, we will be discussing stabilizing improvements. To sustain the gains of improvements, we must understand the concepts of variability and the tools to help us understand variations in process performance. When you embarked on your experiments and learned more about how you and your team understood the obstacles and issues being addressed, the process will experience certain improvements in its performance. These improvements are a product of learning and understanding of the appropriate solutions that would help drive process change. These improvements in the process performance are expected to be sensitive to variability since the team is just discovering the right areas for intervening, but have not fully ensured that such improvements will be sustained. Ideally, what we want to happen is that the changes introduced from the experimentation are sustained into the process and performance becomes stable and perform in a much higher level.
Here are some examples of experimental results to process performance. This is an example of a setup time improvement on a changeover process. As the team embarked on improving the setup time, the team begins to discover the appropriate solutions that would drive process change. As you can see, during the improvement cycles, the setup time begins to reduce. It is an indication that the team is implementing the appropriate solutions. But for these to have lasting impact to the process, the same performance should be replicable for it to be a sustainable improvement.
Here is another example of an order entry process. Monitoring number of errors across time will show if the expected results of process changes is actually achieved. So this is the point where process improvements begin. So as you can see across time, as these improvements are introduced, the number of errors on this order entry process is actually decreasing over time. Here is another example of monitoring of the impact of experimentation to performance, as you can see here. And again, as solution adjustments are introduced to look at how it has impacted the performance. To sustain improvements, the team must be able to understand these variations in performance and if the expected performance can be consistently met and sustained. Thus, we need to understand variations. It is important to talk about variation because it is highly interlinked with quality. When we talk about quality, it is about meeting customer expectations in a consistent manner. Quality is inversely proportional to variability, and the goal is to be consistent in our products, services, and processes. Recognizing variation in processes will help us understand its causes and be able to expect the occurrences. Variation, by definition, is a measure of the spread of data. The amount by which one item, output, or measure differs from another. The shape of consistency actually looks quite narrow. Look at the red curve. As the spread of performance is not as wide as it may seem in the high and medium variability. In this comparison of the dimension of transmissions, both the US and Japan made transmissions have the same mean, right? So they are actually, the mean is on the target. It is in line with the target. But Japan made ones actually has a narrower spread, indicating more consistent performance. In any process that we deal with, variations will always exist. And understanding why these variations happen will help us understand how we can stabilize process performance. The succeeding slides will introduce some principles to bear in mind when it comes to variation. The first one, no two things are exactly alike. Products may start out almost identical, but as one equipment begins to wear or a screw are changing and being replaced, variations start to creep in. But the good thing is, as in the second principle, variation in a product or process can actually be measured. Variation is a normal to process, and this variation tends to increase with time. And as we are able to measure performance, things actually vary according to a definite pattern, making variation quite predictable. A pattern will take shape as records of the measurements are taken and the frequencies of these measurements are plotted out. Which actually brings us to our fourth principle. When things of the same kind are measured, the measurements will tend to cluster around the middle. Measurements will tend to follow a normal distribution where prediction of the percentage of measurements in various sections of the frequency distribution curve can be made. The fifth principle is it is possible to determine the shape of the distribution curve for products made by any process. By making a frequency distribution of the measurements of products made by a process, we can compare it to the specification for that dimension. So we can actually compare if the measurements are actually falling within the specified requirements of our customers. And lastly, variations that are not part of the product or process design tend to distort the bell-shaped curve of process performance or product output. Understanding variation then through a frequency distribution can help determine the process if it is still operating as designed or if it's not. There are two types of variation, special cause and common cause. Special cause is something different happening at a certain time or place, and common cause, it is always present to some degree in the process. Assignable causes are those we can do something about. These special causes are out of the ordinary events that tend to distort the bell-shaped curve. Common causes, on the other hand, refer to chance variation in a process. They are continuously active in the process and is usually built in as part of the process. Recognizing that variation in a process or product exists and that it can be measured is important for two reasons. One, we can use it to understand its causes, and second, we can predict its occurrences. Now that we have an appreciation on variation, we introduce the principles and purpose of control charts to help us understand variations in process performance across time. Control charts help us determine if there have been any shifts in our process due to changes introduced in experimentation, and helps us assess if the changes introduced have stabilized and now been part of the process. Such as in this example, process shifts happens during the experimentation. As testing and adaptation changes, the performance changes across time. And monitoring the latter part can also help us indicate if the improvements have been sustained. So we introduced the concepts of statistical process control, or SPC. SPC employs a statistical method to monitor and determine if a process is in control. It helps teams identify if variations over time are from common cause or special causes. The first step in understanding variation is to plot data in a time order, where we collect data regularly across time. Examples here are measurements on the first 100 outputs, measurements on every hour, or monthly complaints from the past 2 years. Time order data is important as with variation principle 1 and 2, process conditions change over time. Data from one point in time is not always exactly alike to another data point in time. In the first chart here, we can see that there is a drift. If we are not taking data across time, we might miss out on this performance drift because it is not that obvious, right? So if we only have snapshots of data, we might not be able to observe this shift in performance. In the second chart, there are spike points that can be observed, which might be just random occurrences and goes away by itself. But we have the statistical process control concepts and the use of control charts. If we use these control charts, it will help us actually determine if something that is happening is non-random and indicating if there is a presence of special causes. Control charts are time order plots with limits in them to help monitor the performance of a process over time. Control charts is also like a histogram, only that you have it on a timeline. Here are the basic features of a control chart. The control limits, which are calculated, these are determined from process data. And also the center line, which usually is the average, and of course, the data plot across time. Usually, a process is in control and performing normally when the data points fall within the control limits. Any deviation of normality will indicate points that will be outside the control limits, indicating that there might be special causes pushing the process out of control. Just to differentiate, there are what we call specification limits and control limits. Specification limits are customer and engineering requirements that represent what someone wants a process to do. It can sometimes be changed by changing the requirements of the products or service. Whereas control limits come from calculations on the process data. It represents what the process is actually capable of doing. And this can only be changed by changing the process itself. Control charts can help us know when the system has changed. When properly used, the control chart will tell you three things. One, when you are doing something that you shouldn't, so it might be a special cost variation. Second, when you are not doing something you should. And thirdly, when you are doing things right. Control charts can help us analyze, improve, and communicate. Analyze if there are assignable causes for variations. We can use it to improve process by identifying assignable causes and correct them. And it also can help communicate if we are consistently meeting specifications. Bear in mind that there are various types of charts that can be used, and there's two general types of control charts, and these are what we call the variable chart and the attribute chart. Variable charts. This type of charts is used where dimension of characteristics is measured and the result is a number. This might include, but not limited to, the measurement of a critical dimension such as height, length, width, radius, and other measures. And also you can have measures such as the weight of a specific component or the measurement of an important voltage. On the other hand, there is also what we call the attribute charts. The attribute charts are a set of control charts specifically designed for tracking defects, or also sometimes called nonconformities. These types of defects are binary in nature, or it can be answered by a yes or no. Depending on the type of chart, the number of defective parts are tracked, or alternatively, the number of defects are tracked. So examples of defects are paint scratches, discoloration, breaks in the weave of textile, dents, cuts, and other defects that is not conforming to the customer requirements. Now that we have basic appreciation of control charts, how can we see process performance patterns in these? Control charts allow us to view graphically when a process has shifted away from the target and allows us to introduce corrective actions when necessary. So, what patterns should we look for? In control charts, we should look out for points beyond the control limits. These data points outside the limits indicates that there may be assignable cause that happened at that point. We can also try to look for narrowing or widening control limits. This may indicate that some actions have been made to change the process. We also should look out for runs. Too many points on one side of the center line demonstrate shifting in the process. This may indicate drastic change in the process, or it may also indicate measurement problems such as data corrections and sampling. Watch out also for trends. This indicates a gradual shift in the process. This is likely indicating that the process is getting out of control, and an indication of degradation such as wear and tear. When you see data points hugging the center line, this may indicate that some actions and process changes have been made to make the process perform more consistently, and thus may need to revise the control limits. Conversely, watch out also for data points hugging the outer line, which can indicate that there has been a change in the process level, making the spread of data points wider. Cycles can also appear in your control charts, which indicate that changes in the process recur periodically or in cycles. So you have to investigate why is this such that the cycles are happening. A sudden change in the process may appear when changes are introduced in the process. As such, watch out for jumps in the levels of process performance. Lastly, watch out for two populations. If few points are near the center but the remaining points are either above or below the center, this may be a two-population process control, meaning there might be two sets of actions being performed in the process concerned. The patterns shown are indicators that there is something that might be happening in the process, which bears the need to monitor the charts to understand why the variations are happening. For control charts to be useful, it has to be used concurrently with the process, where it is visible, up to date, and used. Control charts can be very helpful when we are trying to stabilize processes. Control charts can help us see whether intentional changes in a process results in the desired performance. It can help teams monitor key processes and identify shifts or changes quickly to help hold the gains made from an improvement. When there are specific patterns observed of process performance, we can use this as an indicator to determine appropriate actions and response to investigate the four special causes. And finally, control charts can help us determine the expected range of values that can help us plan our operations. We would like to share to you three key messages in this lesson. Firstly, Improvements does not stop at just fixing problems, but we need to ensure improvements in performance. Because lasting improvements happen only if processes have stabilized with its new conditions of the changes introduced. We have to see to it that the intentional changes in a process has the desired result by monitoring sustainability of performance. And lastly, key processes should be continuously monitored so that we can identify shifts or changes quickly so that improvements do not revert to the previous performance and that we hold the gains made from improvement.